And we're live. Hello, everyone. Welcome here.
Good morning, good afternoon, good evening, wherever you're from. So thank you, everybody, for tuning in today. Very topical, given that just 2 days ago, it was the warmest day on record. And yesterday was even warmer than that. So I guess it was the second warmest day on record. And so we're going to talk about, climate models and data. Obviously data is the thing that helps us understand anything. It doesn't matter what it is. Data is the key to increased understanding. And so anyone introduce yourself, Dean?
Yeah. So my name is Dean Hintz, and I'm been with SAFE for a while. I work with the Strategic Solutions Group, and I also am the tech lead on our open standards support. And so one of the things I'll talk about a little later is some of the pilot work that we've been doing relating to climate data. Perfect. So yeah, welcome everyone here today, and really look forward to a good session.
Yeah, and I'm Don Murray, one of the co-founders, and I'm excited just about data in general. And so, and I get the opportunity to work very closely with Dean, and so I'm happy to be here and talk about climate change and data. So, Oliver.
Yeah, myself, I work for Tensing, who are SAFE software partners on the FME side, undertaking a lot of work with regards to data integration. And yeah, pleased to present one of our customers and Panagis of Agri Epicenter.
Hello, I'm Panagis Tzivras. I'm a GIS software engineer at Agri Epicenter. I'm really happy to be here with you all. And we're going to talk how we use the FME today to, along with Oliver, how we use to integrate data from different sources.
Great. Awesome.
Excellent.
Yeah, so I'll run through the agenda. So we've just done our quick introduction, and then we'll talk about, understanding climate change data, what it looks like, where to get it, things like that. And then we'll look at who is this, all of this important to. And then we have an exciting story on precision farming that Oliver and Panagis are going to do. And then Dean's going to share some of the OGC work that he's done. And and then climate resilient pilot. And then we'll talk about some of the challenges and follow up with a conclusion and QA. And I think with that, Elizabeth is going to run us through Livestorm.
Yeah, thanks, Don. So just quickly before we get started here, if you're new to Livestorm and you have any audio issues whatsoever, you can click that help button for 4 simple troubleshooting steps on the bottom left. Share your reactions with us throughout with that react emoji button. And then we will have a poll come up with that polls tab on the bottom right. And yeah, keep letting us know where you're tuning in from with the chat. We love to see where everyone is around the world. And if you have any questions throughout, we do have Kaylin and Jenna joining us on the back end to help answer those. And then we will have live Q&A if time allows at the end as well. If you'd like to download the deck to follow along live, you can click that download button on the top right as well. And with that, I will get our presenters to turn off our webcams just to save on some bandwidth for the remainder. And I'll pass things back over to Don for our chat storm here.
Yeah, so we want to begin this with a chat storm. And so in the chat window, just type what your biggest data challenges related to climate change impacts. And it's kind of fun to see what everybody types in. So yeah, okay, so do that now.
Lots of people typing. That's great. Thanks, everyone.
Okay. I think that's it's good. Looks like a lot. I mean, it looks like the data topic is very, very relevant, as a lot of folks are identifying that just knowing where the data is, getting access to the data, and understanding where the data is the key. And as understanding anything, that is always the first thing that is important is where do I get access to the data? So, and what kind of data do I need? So good, awesome. So yeah, so with that, a little introduction about Safe software. So data in everything Safe does is around the data, making the data available to you so you can gain understanding and insights into any challenge. And in this particular case, there's a data cube that you're going to see. So I'll just point that out now and then watch for the data cube, and you'll see us. We'll explain what it is and why that really helps you understand, data measurements over time for any particular area. When it comes to data, FME is we support more data than anyone, and I've sort of pulled out again. I put circles on ones that are interesting from today. I mean, we integrate all the data, but the ones that are really interesting today is like raster, NetCDF you can view, and ZAR is essentially raster with a time slice for a different period of time. And a raster, as we know, doesn't need to be imagery. It can be any measurement. And so that's really you can see the picture of the data cube up there. IoT and sensors is another one. Pay attention to that in the use case that's done by our friends at Tensing. And then, of course, cloud native ZAR is a cloud native data cube format. And of course, web services are being used for sharing data and things like that. But those are kind of the ones that are the most relevant for this webinar.
I was just going to mention, Don, like the web services and cloud are both prominent here. Yeah,
absolutely.
For sure.
Yeah, absolutely. Yeah. And just a little about Safe software. I won't run through it, but we use we've been around for a while, and this is what we do. So, okay, and our platform. There's three things really form, which is the old desktop product. That's where you start all your workflows, and then you want to automate them or make them available to a wide audience, and that's really where flow is. It creates the automation, the ability of the data to flow to wherever you need it, and then we also have a cloud-hosted platform. So if you want to learn anything more about that. And our differentiators, really, the largest ecosystem is a big one. There's no other data integration tool anywhere that does all the data types that we do. And also, you get it all. We don't sell by connector. When you buy FME, you get everything now and in the future. And of course, you can deploy it anywhere. And our restaurant model is something we're really proud of. We really work hard to provide not just a great product, but also great care for our users, our partners, and everyone else. And so with that, Dean, I'm going to pass it to you in the Flash demo.
Okay, great. So I just opened up that data set, but I didn't actually set the coordinate system. So when I put in the coordinate system, you can actually see the data. And you'll notice one thing that's interesting about this data set is that, it's got literally hundreds, probably close to 1,000 bands. So each of those bands is basically another time step. And so that's essentially what we're talking about when we talk about a data cube. That's the NetCDF. So that's a fairly complex data set that most of you may not typically work with on a day-to-day basis. And so a much easier way to look at that would be, I'm going to pull in some GeoJSON and grab, this is the feature collection URL. Paste that in there, and I've got these parameters saved from before. And so basically, I'm just looking for the precipitation by months, and I'm looking for particular extent and time range. Try that. And so it's just going to go to my service, a REST service, and deliver some data. And here you can see the precipitation for Winnipeg for basically the next 18 time steps. And so right now for 2023, it had 21 millimeters. If I jump ahead to May or June, that's up to like 74 millimeters. So I just wanted to show you quickly. And then it even has a bit of the metadata around where did this actually come from. So it's this bias corrected downscaled for Canada. And there's some, NRCan and various other background information about that data. So that's pretty much it. I just wanted to show you really quick. So this is a very simple view of the same data set with a point representation rather than that data cube. Okay, so I'll just steamroll ahead here. That's the URL I used to access it, and those are the query parameters. Yeah, so basically the goal I'm showing there is simply to make that data more easily consumable. Most applications can handle GeoJSON. So that's just the same screen you just saw. So let's, before we dive in too much into FME, let's just talk briefly about climate model data and what are some of the challenges around that. So right off the top, there's a fair bit of challenges with the terminology. Even in some of the metadata there, you saw terms like bias corrected and CMIP5. So there's all these different terms, and you don't necessarily have to understand them all, but you do. Some of them are pretty important if you want a reproducible results. So if you want to be able to pull data, you'll want to know, oh, is this a low, medium, or high emission scenario, for example? And then finding the data, as some people pointed out in the chat, there's a huge volume of data out there. Finding data that's going to be relevant to you and your location at an appropriate resolution, that can be a bit daunting. And then once you get the data, how do you actually simplify it? So as I'll bring up on more than one occasion, there's this sort of Goldilocks principle of, you want just the right resolution and the right amount of data to solve the problem or support the decision making at your local level. So too much data and you're overloaded, oversimplified, and you don't have enough information. So just before we dive into some of the details of climate change data, maybe Elizabeth, we can run this quick poll. I'm quite curious from our audience how much you've worked with this type of data before.
Yeah, so just head to the polls tab on the bottom right there and cast your ballots. Give everyone a few moments here.
Yeah, I'm really curious to learn what kind of range of experience you have with working with climate data.
So Dean, it looks like the majority know they exist but haven't used them. And then also quite a lot of folks that didn't know they were available or how to access them yet. Okay, so yeah, I've just flipped over to that view. So yeah, it says 47% knew they were out there but haven't used them, and then 26% didn't actually know how to access them or what's there. So yeah, I mean, first for me working on this OGC pilot, it was certainly a learning curve finding out what the data availability was and how to access it. But yeah, well, that's why we're here, and we can certainly help you out with getting at and extracting from that data. So I'll just keep moving on then. Thanks for the poll there. Thanks for your responses. So in terms of climate data, the focus that I've had recently is around disaster management and also managing potential climate change impacts. So from the disaster management perspective, we've had lots of data from historical hazards, and then over time we've gotten better at real-time sensors, so we can detect things like a surge in stream flow that might trigger a flood warning, and we have imagery which would show fire and flood extent. So the challenge we're looking at today is how can we improve our awareness of what some of the future risks might be? And so one way of doing that is ingesting some of these outputs from different climate models. And the goal here really isn't so much to make a specific prediction, this is exactly what will happen, but more to understand a range of different scenarios and how resilient are we to those kind of changes. And the main challenge here is that we don't have the climate service and standards and meteorology. That meteorological data is well understood within that community, but not very well understood in the domains where people are likely to be affected, or let's say at regional government level. So just a little bit about terminology. I mentioned emission scenarios. So that's that RCP 2.6, 4.5. So those are those terms I'll define it more fully later, but that's essentially how much greenhouse gas is anticipated to be emitted
low, medium, high. There's the model type, so the regional models and the global climate models. And then you have things like the extent, so both in space and time. What's the location range and the begin end year, and then the time steps and resolution. Day, month, year. Square kilometers, that sort of thing. And I mentioned, and at the bottom there was mentioned the ZAR and NetCDF. Those are sort of the two main formats used for those data cubes. So in terms of data sources, we have links, and the deck will be available. I think actually you can probably even download it now, and we can certainly help you with that at the end. So the data I got that I worked with was predominantly from Climate Change Canada, and so that's the web page there that I used. And then there's also this there's a number of USGS threads data services, and the interesting thing here is when you put that together, you build a URL. So FME actually could easily compose that URL if you wanted to automate that data extraction process. Just an aside. So RCP, these are some of the key model terms to keep in mind. That stands for representative concentration pathway, but the actual specifics of what that means isn't that important. It's basically the 2.6 is a low, low emissions scenario, and then it's progressively higher. So 4.5 is sort of a moderate business as usual scenario, and then you have some higher emissions. And so you can see that graph there, and there's links to the Wikipedia article. It's got some good background on that. And though I did want to mention CMIP5, so that's the generation. So that's back, 5-8 years ago. And then there's CMIP6, which is currently being refined. So those are just different generations of climate models. And the BCSD stuff, that's just the method for downscaling. So if you want the same result, you don't necessarily have to understand all the specifics. You just want to say, okay, I'm dealing with RCP45, CMIP5, and BCSD, and then you'll get the same result. So there's that Manitoba data cube in NetCDF. We already saw that in the flash demo. And so what might we use that for? Well, we can get temperature data and look at and analyze that for heat waves, maybe evaluate that against buildings and heat island effects, or look at the heat wave. Let's say we have hot spots, we could check that against population or critical infrastructure, and look at change over time. And the same thing, we can do similar things with drought, and we'll see some examples of this later of how do we feed drought models with climate data and look at different trends. So who is this important to? I kind of mentioned planners, managers at the local and regional government level. And certainly, that's kind of the most obvious. There's also engineers that are responsible for supporting our critical infrastructure, like utilities and transportation, government, who have to maintain everything from health or environment to public safety. And some of those that you may not think of as often are in the insurance sector, the financial sector, because they have to quantify future risk in order to guide their decision making. And then all of us, because we're all impacted from climate change. So I'll pass it over to Panagis and Oliver from AEC and Tensing, and we're going to hear a bit about how they're using real-time sensors to monitor climate data, which seems to be very essential in our changing climate times. Thanks.
Yeah, thank you very much, Dean. So, from our side of things, I think the webinar is incredibly timely, actually, because in the UK, June was the hottest June on record. And when we're actually putting these slides together and looking at some of the sensor data for some farm data sets we have, it's really quite evident that you can see it, the soil moisture drying out, and then these big kind of increase in surge when the thunderstorms rolled in at the end of the month. But yeah, to go back a little bit, it's been really good to work and support AgriEpi help them to integrate and collate all of the different data that they gather from all of a range of different sensors. And yeah, ultimately it's helping to mitigate the risks that climate change pose. So yeah, I'm actually going to hand over now to Panagis to give a little bit more background into AgriEpicenter, and then I'll come back a little bit later on to walk through an example of one of the workspaces that we helped to build. And so yeah, over to you, Panagis.
Thanks, Oliver. So first of all, let's chat about AgriEpi for a bit. Then we're gonna go and see how agriculture is affected by climate change, and then we can see if and how we, as an AgriTech company, can help mitigate the climate change effects. AgriEpicenter was initially created in 2015 and established over the following years. Although I, as a data engineer, GIS software engineer, I come from a completely different background. I found the challenge to work with new data sets from different sources and formats, and colleagues also from completely different backgrounds, really exciting. At AgriEpicenter, we use innovative technologies to try and improve agricultural efficiency and precision, to try and help to promote sustainable food production practices that help to mitigate the impacts of climate change. We have three main philosophies, three pillars we work on. First of all is our purpose. We believe in a world where engineering and precision agriculture technologies, systems, and ecosystems are optimized to get what? In order to maximize the AgriTech sector contribution to sustainable food production supply. Then we have our vision, which is to help and transform, drive growth, and support innovative solutions to help farmers and agri-food businesses become more sustainable and profitable. And finally, our mission, which is our work, is about providing scientifically robust and commercially viable solutions to improve productivity and sustainability within the food production system, focusing on using new technologies, robotics, autonomous solutions, and of course using the data to make harvests as consistent as possible. Now let's have a look who is AgriEpi collaborating with. There's quite a range of key collaborators, all with their own data requirements and needs, from farmers, food suppliers, agri-food industry, and the UK government to engineers, scientists, investors, and even some small startups. All of them have their own data needs. To cover these needs, we needed the flexibility of FME to deliver the data that we had collected in a range of different formats. Now let's take a look at our topic, how is climate change affecting agriculture? We have a direct influence in crop growth and yields due to the changing precipitation and temperature patterns. Also the extreme weather, extreme events like droughts or floods that put risk in crops and infrastructure. We also have the changing distribution of different and the severity of different pests and diseases, which also affect crops. And finally, we have the socioeconomic impact, where we have risks on livelihood and security and food security of farmers and local communities. Now, on the right-hand side, we can see an image that shows a healthy corn crop versus a distressed crop. We are monitoring the health of crops through IoT soil sensors, which is one of the ways to mitigate the effects, but we'll talk about this in the next slide. Right, so we have identified 5 ways with which AgriTech can help mitigate the climate change effects. First of all is the efficient resource management, where we implement precision irrigation and nutrient management aided by sensors to decrease water consumption and prevent runoff. Then we have the digital tools and data analytics, where we employ remote sensing, drones, and other sensors for crop performance monitoring and early detection of pests and diseases. And then we have soil monitoring, which is we are constantly tracking soil moisture, temperature, pH, and nutrient levels for optimizing the irrigation and fertilization methods. Of course, precision farming, which will leverage data from the various different sources for precise farming and adaptive management of the farm. And the last one is the harvest management. We monitor crop growth, yield, and quality for improved harvest planning and post-harvest management. And there on the right-hand side, we can see one of the sensors we're using. This one sends data for temperature, humidity, wind, and it's based on a potato field in one of our research farms. Also, all these sensors are geotagged, so we have the special component as well in there. On the next slide here, yeah, right. So climate change can impact not only crops and farmland, but also herd health. There are many different systems we are currently integrating with FME, like Beef Monitor, which gives us cattle weight data, Full Wood, which is real-time dairy milking data, and Uniform Agri, which gives us herd health and treatment data. And we have much more integrations to come. Now, on two of our research farms, we are also testing Fitbits for cows. You can see that on the right-hand side, how that looks like. And LiDAR field surveys we're also preparing. Now, let's focus on the data set we have now from IRRIMAX. Now, we have a network of high-precision soil sensors, which sends us data for soil moisture, salinity, and temperature. We have over 70 IoT sensors across 20 farms, and we're getting data from January 2021 and on. And this allows real-time monitoring of water use for precision irrigation. And IRRIMAX Live exposes the sensor data via an API, so it's accessible. And at the bottom, you can see the chart we're getting from one of our sensors. Each of the columns there, the dotted lines, is a week. And in here, we can see what Oliver talked about in the first slide. We can see the record hottest June in UK, where we have that dip. And on the right-hand side, we can see an image of a cross-section photo of the probe we're actually using, where you can see the different sensors in different depths. So we have 5 different sensors for 5 different depths. And now, over to you, Oliver.
Yeah, thank you very much. Thanks, Panagis. So it's quite interesting. There's a whole range of different sensors, and they all have different platforms for their data delivery. So it's actually been quite a challenge in some cases, extracting data from either a farm's computer systems or just scraping data from web pages, believe it or not. The IRRIMAX API was actually one of the easier ones to handle because it had a really nice API interface. But we at Tenzing helped AgriEPI effectively collate that data through a range of workspaces to pull the data into a centralized repository, which was in our case, or in the case of AgriEPI, Postgres database. So this is all powered by FME, both using a range of FME form workspaces, but also using FME flow and the scheduler process as part of that. So now what we'll do is we'll jump to a video and I'll kind of give you a quick step through as to what that looks like in terms of a relatively simplified version of the workspace we're using. So the first step here is that we go to the IRRIMAX API. So we do that using HTTP crawler. We authenticate and we ask it to retrieve back all of the loggers that it has information for. It actually has 71 loggers at the moment, which we've obtained property information like its location, spatial location, and yeah, that helps to show that it's situated across a number of different farms. Yeah, if we carry on the video now, yeah, you can see those property details for all of those different sensors. Once we go to this next section, what we're doing is we are going to the Postgres database where the data is stored, and we're finding the last date that a record was entered in. We do a little bit of manipulation of the dates and times so that we can structure the date and time request from the API to only return back the latest data that we haven't captured within the Postgres database already. And so, yeah, we do that through another request using the feature reader this time. And yeah, if we just carry on through the video a little bit more, we'll see that it's basically returning back both the pressure and, both the soil moisture, salinity, and temperature information. And yeah, if we carry on just a little bit more, yeah, so that's pulling in and getting those readings. And then once that's complete, what we do is we just do a final cross-check to ensure that the data that we are receiving, we haven't already captured. So it's just like another double check. Here we're just constructing the string of the from time and to times. Here's some of the sensor data. As you're saying, it's quite a lot of information that we're returning back for each of those different depths that those sensors work at in the soil. And then, yeah, it outputs to the database, and if there's any kind of record issues, that's handled by feature writer 2 and put into a separate table just for any investigations. So this is quite a robust system, which means that if there was ever a scheduled task that was to fail, it would always just know what the latest or the last record of data it had, so that it can go off and collect that data again or re-request the latest data. So I mentioned there's not just the workspace that we've been working on, there's also FME flow that's part of the picture. So we're going to jump now quickly to that just to see a very simple automations that we've got. So we have that job running on a scheduled basis, and then that's calling a couple of different workspaces to check when the latest data was from, and then to upload to the database. So yeah, that's the end of a little summary. And just finally to conclude, so really just in summary, we are, AgriTech is clearly now built on a range of smart sensors. There's still a real challenge to integrate with them. These sensors, the data is exposed in a range of different formats, which makes FME the perfect tool to use to pull those data sets in. Many times they can be in real time. It's really helped to kind of centralize all of that data together, and yeah, the opportunities to be able to expose this data to all of the different people that all of the different key collaborators that Panagis already explained, from scientists and academics through to engineers and wider industry, show that producing a kind of self-service delivery of this data going forward is the way to kind of make sure that that all of the data collected and all that sensor information is exposed as widely and as accessibly as possible. Yeah, thank you very much.
Yeah. Thanks, Panagis and Oliver from AEC and from Tensing for that great overview of that precision farming solution. Yeah, and I just wanted to mention that I think that's amazing, all that real-time data that you're collecting, because that not only can that be used in future research, but I could foresee having maybe workflows that watch for certain thresholds, and when those are exceeded, generating alerts or alarms and that sort of thing. So just in terms of supporting climate mitigation and resilience, I could see that being key. So I'm going to jump quick, and I'll try to roll through pretty quick. If I go too fast, the deck will be available later, and you're always welcome to ask questions, and we can follow up. I'm going to jump right now into the OGC climate resilience pilot that I've been working on, off and on for the last 6 months or so. It just wrapped up. There's a link there for more information. And And we're going to look at, okay, we just saw a really good example of some real-time climate data and how that can support a resilience as, as we see the climate around us change or dealing with different, more extremes. Now we're going to look forward to how can we build resilience into our planning. And so better understanding the range of possible climate scenarios and what their impacts might be in order to better prepare and compensate for them. And as I mentioned earlier, one of the goals of this pilot was to, first of all, promote resilience. Secondly, to expand the audience in terms of, people knowing about climate services, and then also promoting OGC open standards and spatial data infrastructure approaches just to make it easier to exchange data. Because the reality is, to cope with these climate impacts, we're going to have to collaborate. No one group is going to be able to solve everything. And so that ultimately is also about building that community of stakeholders. And so that's, I welcome you to tune in to what OGC is doing in that area. Just to mention, that whole pilot is sponsored by Natural Resources Canada, US Department of Homeland Security, and NOAA, among others. So just this looks familiar. I showed this earlier. I won't spend too much time other than to say, here we are back to our friend, the data cube. And so in particular, we chose the business as usual scenario, RCP45, and the regional climate model data for LA and for Manitoba. And then basically that gives us about a 10-kilometer grid in a monthly time step. So our goal there is to extract that data and make it easier to access and consume downstream for other applications that will do analysis and generate impacts. So this is basically the workflow that the FME workspaces do, and it kind of follows the same pattern. You'll see this repeating. Basically, we've got this large data cube, as we saw earlier. It could be 1,000 or more time steps. We explode that into individual grids. We set parameters, IDs, time steps on each of those grids. And then we compute stats either by band or by cell. And then ultimately, we found that downstream, it was easier to transmit vector data. There were more clients that could do something with the vector data. So then there's some kind of conversion and aggregation going on there. And so this is one of the earlier workflows. And what it's doing is exactly that workflow I mentioned, with the last step of generating areas, or sort of in the raster to vector conversion. And some of the key transformers used there, raster band separator is basically what takes the data cube and breaks it into individual bands or grids, one per feature, because the data cube comes in as a single feature, and you can see after the separator, you got 960 coming out. And then we have the raster stats calculator for computing stats, classifying the data with the cell value replacer, and then the geometry conversion. So just a sample of some of the values there, some of the parameters, and I'll just highlight the mosaicer because that's very key in basically taking a bunch of bands, and by a year or by a certain time step, we can compute stats like maximum, minimum, or even sum up the values. And the classification is done in the cell value replacer. In that case, I'm classifying temperature. So this is an example of looking at max yearly temperature for Southwest BC. So that was some of our early testing. I had some data for the BC area and crunched that. And normally, as we saw earlier, when you're looking at a data cube, everything's just piled up, and you only really see the top layer. Here, using a group by on the inspector, we can break it up by year. And then I had essentially a client pointing out a geodatabase, or actually a geopackage, I should say. And so we ran this query of what is the average daily max for the month when it's greater than, give me all of the polygons where the average daily max for the month is higher than 25C. That yielded some interesting hotspots in the BC interior, Fraser Canyon area, which corresponds to the same location that ended up being the hottest temperature ever recorded in Canada at 49.6 C in June of 2021. Unfortunately, a week or so later, that whole town burnt down completely due to wildfire. So you can see that those risks are very real. And it was just interesting that that query, coincidentally seemed to pick that out of the climate data. Now, when I applied a similar approach to Manitoba, it didn't work out so well because we get these large areas, and that's probably due to the low relief. So we get much more gradation in temperature because in BC with the mountain ranges. So we kind of had, based on feedback from the end users, they were like, well, we don't really need these polygons. We just want the actual point data. And while normally we don't like to convert an entire grid just to points because there's a huge volume, but the climate model data is not that high resolution at a 10K grid. You can see here, we actually end up generating 2 million points, but FME can handle that just fine. And when we're writing that to a database, you're never going to stream out all of the data at once because people are going to query it by time and spatial extent. So here we're basically taking the data cube, splitting it out, converting it to vector, computing statistics, and then also combining it with some record level metadata and generating temperature and precipitation. And so here we can see the precipitation value for Winnipeg in June, which is about 70 or 80 millimeters. And so this gets published as a test service, an OGC API test service, and that made available to other participants on the pilot. They can now have the flexibility of entering some of the parameter values and even the environmental variable value ranges that they want. They can choose a layer for precipitation or temperature and then what ranges they're interested in and get the data back for that. Just for comparison, again, one of the early services generating temperature bands as contours versus points. And you can see the band itself is not very useful because it covers such a large area. We get a lot more detail just giving them the points. And yeah, so that just shows the flexibility of FME and rapid prototyping. And so these are just some of the indicator queries. We can discuss this stuff in the Q&A, but what you might be able to get out of climate model data to support heat waves, drought, fire. And then we also have to look at how do we, which variables do we have to extract and what kind of statistics do we need to compute and how can we expose those as parameters. So we certainly haven't solved all these problems. This is sort of scratching the surface, but I think we've made a good start. And so this is, again, a similar GeoPackage querier. In this case, we're doing a better job of pushing the spatial extent and feature limits to the feature reader, so we only get the data that we need. And again, there's precipitation, I believe, for June for Winnipeg. Now, this was ultimately fed to other participants in the OGC pilot. And I'd like to thank Samantha Lavender from Pixelytics for giving us some of their results. And you can see the raw precipitation values are on the top right of that chart. And in the middle where the red bands are, that's actually where her tool is forecasting drought. And what's really interesting about this is she has historical data up until basically now. I guess the historical data ended around March because that's when she was integrating the data. And then she took the climate output from FME for the rest of, from now forward. And it was actually seamless. There was no discontinuity there, which we're a little bit suspicious of, but we're just going to go with it for now. And so anyway, you can see there was a bit of a drought last fall. It looks like we've got plenty of precipitation, maybe even, some potential flooding. And then in the following, I guess next summer, we might anticipate drought. So changing gears, we'll just quickly look. My last example here is for LA and for visualizing the effects of climate change on the landscape. And one of the big challenges with climate change, it is a global phenomena. And so it can be rather difficult sometimes to understand, well, what are the effects going to be on the ground? And it's one thing to feed a data model and get some points out of it. but it's something else to actually say, well, how will this affect the landscape? And so sometimes just communicating that when people are trying to do planning and support different policy changes, that can be a big challenge. And so I really like this particular example because it's all about visualizing what are the effects of climate change on the landscape, in particular on the vegetation. So again, we're doing RCP 4.5, which is a business as usual scenario, but this time for the LA area from a USGS thread service. And we're using that raster mosaicer first to compute the average historical, and then you use that as to find the delta, the change in precipitation. So we didn't have a drought model to feed in LA, so we basically went with change in precipitation, ultimately deriving an actual index, which is sort of like, is it 10% wetter, 10% drier? And then that is fed into the vegetation model, which supports the visualization. So this I find is a little easier to follow than that text-heavy previous slide, because this shows that FME can be used to take, let's say, 1950 to 1980, 30 years of historical data. We just take all the Januaries and average them. And you're not just averaging the total for LA, you're actually averaging every grid cell. So let's say every 10K grid cell, what was the average precipitation in January for that 30-year range? So FME is quite simple. I'll show you in a minute how we did that. And then all we do then is take the future time steps and difference them from the historical mean to come up with a precipitation delta. And that can be normalized by dividing by the historical average. And so this is the workflow, and the key here is using that raster. So yeah, basically the bookmarks at the top are extracting the historical grid and then computing that average. So you get 12 time steps. And then what we end up doing is we just replicate as many time steps as we need for all the years that we're processing. That's why we go from 12 to close to 400. And then we read the 400 or so future time steps, and then we basically do the differencing and compute our stats, merge in the metadata, and write that out to GeoPackage, and then that gets served up as GeoJSON. So again, the FME output here is a bunch of points, and that, it's got the information, but it's not that visually compelling. So the folks at LabVerk were great to work with, and they actually took that data and used it. Tim Dapper in particular worked with him, and they used that in their visualization, landscape visualization, to change what kind of vegetation you have. So you can see the present day, you've got a palm tree in the foreground, and that one disappears because of its climate tolerance, environmental tolerance. It gets too dry and it no longer can survive. So here's just a few quick screenshots. So that's present day, that's future using a particular mitigation. So here's the do nothing scenario where 2020, and you can notice that you have a lot of these, I call them Dr. Seuss trees with a little sort of almost like a cotton ball on top. And those get fewer and fewer as we go into the future. This is sort of the do nothing scenario. And scenario B is where we swap out those Dr. Seuss trees for these purple ones. And over time, we get more and more of those. So even though it's dry, we've kind of mitigated the effects, and we still keep a relatively green, enough greenery in our urban space. So just to quickly sum up on that, working in the climate and disaster pilots, stakeholder feedback was critical in terms of figuring out what type of data and stats they need. We believe open standards are really important to support because it makes all these tools interchangeable. We were able to extract data for Manitoba and for LA, and that was really helpful. And, in the future, basically adding those query parameters help the end users to have the flexibility to make the queries that they need. So other things, I won't go through all of this, but we're also going to look at data in the US Northwest. Ultimately, we're going to add other layers, other themes such as soil moisture, which will be useful for agriculture. And then also provide perhaps other format options like cloud native or ZAR, and test some direct connections, because as you saw earlier, you can actually compose URLs in FME and maybe talk directly to the APIs. And if you stream that into ZAR, you'll only stream the data that the client needs. And there's also ways of combining your data with high-res local data like DEMs to get higher resolution output. So yeah, there's lots of lessons learned there, but we believe that it's critical to basically provide people with more avenues for accessing climate model results that are GIS friendly or more interpretable in the tools that people are used to working in. And there's always a bit of that Goldilocks principle of getting this, simplifying the data, but not simplifying it so much that you're losing the essential information. And finding the right geometry types and data structures are important, and ultimately empowering the end users who are going to be your domain experts. And again, the goal isn't to make climate predictions, but to just provide a data pipeline, and then people can better understand what some of the range of possible scenarios are out there. So these are, I'm not going to go through all these questions, but this is just all around what sort of climate variables do you need, what impacts are you most concerned about, and how do you think the data should be summarized. So we would just welcome this as a dialogue in the Q&A, and you can always contact us later for follow-up. I just have these slides as a reference to some of the flood modeling that we did in the Disaster Pilot 2021, which you can read about. And Elizabeth, if you can just play that for 20, 30 seconds, and you'll see that basically we took a similar flood model output from the folks at RSS Hydro and Dartmouth Flood Observatory, and we're able to kind of make a bit of a movie out of that. And through HSR Health, through their portal. And so that was pretty cool. But that could certainly be done for a future time series as well. Okay, next slide. So so that was basically supporting routing, transportation routing around flooded areas. And this is just a visualization of flooding in Winnipeg. And I'll just flip over quick. Back to my other screen. Yeah. So yeah, I mean, this is just as an example of, if you haven't seen this before, this is firesmoke.ca. This is not, we're not directly involved in this data, but this just goes to show the amount of data out there is really exploding. And, so there's obviously the effects. We've got fires across half of Canada, and that's been a big issue for things like air quality. So there's more and more data out there, and it's just a matter of how to ingest that and utilize it. And we've got a number of customers that that we've been supporting in the areas of, let's say, wildfire management. So just to summarize then, before we go to Q&A, we showed that we can combine past, present, and future data to better assess climate change risks. And we've got that back and forth for the Goldilocks principle of doing sort of the optimal level of data simplification. And agile prototyping was really key, as well as open standards. And ultimately, we believe that publishing and evaluating a range of climate scenarios, we can explore more mitigation options and better prepare and improve our climate resilience. So I don't know if Don, you wanted to mention a couple of next steps.
Sure. Yeah. So thanks, Dean. That's great. And so this is a good survey to show you what some of the understanding you can get. At the end, you're going to see the email addresses of the 3 other presenters, and please do contact us. I mean, that's really one of the goals, is to keep the conversation going. If you want to try FME for 90 minutes, whether you're a new user or an existing.
Oh, it looks like we might have lost Don's sound there.
I'll keep talking, and Don, you can jump in if your sound comes
Sure.
back. Are you there, Don?
Yeah, I am. So yeah, and some of the resources, there's an ebook, Academy to learn more, and a knowledge base, of course, and join the community, and you can interact with us and users from around the world. And then we have a long list of upcoming and on-demand webinars. So if you want to watch this again or share it with somebody, it'll be on safe.com/webinars. And Dean was kind enough to compile a good set of climate change resources. So take a look at those links too. This slide deck will be made available, as Elizabeth mentioned. And and with that, I think, everybody's invited to Bonn. We know there's folks around the world here. So Bonn, Germany, September 5th to 7th. Dean will be there, I'll be there, a host of people from SAFE will be there. And it's done with our partner, Conterra, who's based in Germany. And Tensing's going to be there and is a big sponsor. And so it's going to be a great place to come and talk about data. And and if you're in the community, you can get your community badge for attending. And yeah, Dean, I think now we some Q&A.
Yeah, great. Thanks, Don. And thanks everybody for taking the time to spend with us. So do we have like from the folks watching the Q&A any highlights in terms of the questions? I guess we could always scroll through.
Yeah, it looks like we have a hand here.
I did notice, I'll say off the top from the last question, there is a lot of we certainly admit there's a lot of uncertainty with climate projections. So we're in no ways endorsing one specific, model type and, model result. But, being able to, that's why we think it's important to be, once you have a data pipeline like this, you can easily evaluate sort of low, medium, high emission scenarios and see that your infrastructure is going to be resilient. Mm-hmm. And, I was at a workshop last week for the disaster pilot hosted by AGC, and I had a great conversation with some of the folks from Manitoba Hydro, and that's exactly what they're doing. They're looking at a range of scenarios so that even though we don't know exactly what's going to happen, we will make sure that that the systems that we have are more resilient.
Yeah. Yeah. Great. Awesome. So yeah, we're at 9 o'clock now, and so thanks Oliver, thanks Panagis, and Elizabeth and Dean, and everybody who came to the events. And please remember, this is just the beginning of the discussion, so please really do reach out. There you go. There's all the emails of the folks who are on the call, and so please do reach out. We love talking about anything data and climate change, and is just one of those things. And also don't forget to fill out the webinar survey. So thank you so much, everybody.
Thanks everybody for coming and for your interest and great feedback. I just encourage you to go check out what some of the climate data services that are out there, and see what you can make of it. And if you need a little bit of support, let us know and we can give you a hand.
Yeah.
Fantastic. And if we weren't able to get to your question live, we'll certainly follow up on that. So thanks everyone for the questions, and hope you all have a wonderful rest of your day.
Yeah. Thank you.
Yeah.
Bye.
Thanks so much.
Yeah. Thanks, Oliver, and Panagis for help, participating today. It was great. Really loved your presentation.
Yeah, really appreciate it. Yeah.
And thanks everybody for tuning in.
Yeah. Thanks everybody. Bye-bye.
Bye for now.
All right.